Here's a problem involving displacement and vectors. Okay, we've got a hiker who travels 15 kilometers at 30 degrees north of east. Let me draw that vector. If I put a dot for the beginning, my reference for this vector is east. We have to go north of east. So we're going to the north by 30 degrees. The vector that she traveled along is on that angle. There's her displacement. Then she turns and travels 5 kilometers west. Okay, let me try and move this text downward. So I've got room to show her westward. All right, so let me take my pen. 5 kilometers to the west. Finally, she turns and travels 2 kilometers north. Wow. Calculate the magnitude and direction of her total displacement, her resultant displacement. Well, she is ending right here. She started at the beginning. So the total displacement goes from the very beginning to the very end. And that resultant displacement, we could call it, delta R, or sometimes just capital R we might see. And okay, that's what we have to find. Now, this is a really complicated problem, right? And I don't really like seeing, it's nice to have the picture here, but I find it really helpful to separate these out. Here's what I do. I say, we've got this first displacement, 30 degrees. We are adding with it this second displacement, 5 kilometers. We're adding to that this third displacement, 2 kilometers. To find the resultant, we need to know the total x-axis displacement. I use delta for change in x, change in position. The total delta x is going to be the first delta x from that displacement, plus the second delta x from that one, plus the third delta x from that one. Well, there is no x displacement when you go north, so this will just be 0. Then we'll do the exact same thing for the y-axis. We'll look at each of those 3 displacements, figure out how much on the y-axis she traveled. All right, let's get started. Well, this first one's at an angle. How much of that 15 is on the x-axis? How much of that 15 is on the y? Or in other words, how far on the x does that 15 carry her? How far on the y-axis does that 15 carry her? The answer to this we find using our trig functions. So katoa, the x is adjacent to 30. And we have a formula, adjacent equals hypotenuse cosine theta. So right here, I've got 15 kilometers times cosine 30. The opposite leg, that's the y-axis in this case, is found with sine. Okay, we now know delta x1 and delta y1. Let me write that in. This first delta x is positive because it's eastward, 15 kilometers cosine 30. Okay, what's the x displacement from this? It's all of it, -5. I made it negative because it points west. Here, that's north. There is nothing on the x-axis, 0. Okay, now we go to the y total. She's traveling north. How much? 15 sine 30. There's no y-axis displacement here because it's purely to the east. That's 0. And finally, at the end, that's 2 kilometers north, so it's positive. Whoops. Let me move this over to the side. Okay, hang on. So I have room for the answers here. And what did we say here? This was positive 2 kilometers. I get out my trusty calculator, I make sure I'm in degrees mode, and then I do 15 cosine 30 minus 5, 7.99 kilometers. Down here, I've got almost the same thing, so I'm gonna click second entry. Then I'm just gonna change this to sine, and then I have to I'm not subtracting 5, I'm adding 2. 9.5. Notice that came out positive, so north, and this came out positive, so east. Finally, I draw the total x and the total y. When you add up these three displacements like this, on the whole, she's traveling to the right, or east, 7.99, and going north, 9.5. So let me draw that in a new picture. Here's delta x total, 7.99 kilometers. Here's delta y total, 9.5 kilometers. So what's the total resultant displacement? It's the hypotenuse of the delta x total and delta y total. So we can use Pythagorean theorem to get the hypotenuse, and I believe this comes out to 12. A squared plus b squared equals c squared. And we can use tan of theta equals opposite over adjacent, 9.5 over 7.99. And then we have to isolate theta, so we divide both sides by tan, or inverse of, we multiply by the inverse of tan. And here's how we write that. 9.5 over 7.99. That's the way to show that on our paper. And what do we get? Second tan, 9.5 over 7.99. Whoops, 7.99. 49.9 degrees, that's going to round to 50. And then I look at my angle. This angle mark has to point to the vector, right? The hypotenuse, it points to the hypotenuse. So from east, or of east, we are going north. East is our reference, we have to go to the north. That's where the little arc here is pointing to the north from the east. And that's our answer. Now, number 4 is a very similar problem. We will still use delta x total equals delta x1 plus delta x2. We will still use delta y total equals delta y1 plus delta y2. But instead of finding these, those values are given, and we instead will be finding those. So we'll have this, and we'll have to calculate those second displacements. Okay? Let's see how that looks in practice. A hiker travels 20 kilometers north. There it is. Then she turns to the north of west and travels in a straight line to the final destination. Okay, so I'm adding some unknown vector. And when I add those up, what do they equal? Her overall displacement, that's the resultant, is 50 kilometers at 40 degrees north of west. So let me draw the resultant. When I add these up, I get north of west, My reference is west. And from west of west, I have to go 40 degrees. And the vector points along that angle, 50 kilometers. So yes, look at these equations. We can find the total x because we know the resultant. We can find the total y And we can kind of work backwards. If we look at this total y, part of it comes from the 20 kilometers. The other part will come from this vector. So we know this, and we know this. When we look at the total x, which we know, part of it will come from, well, there is nothing on the x-axis. That's just 0. So all of this delta x total has to come from delta x2, the second displacement. Okay, let's see how this works in practice. How do I find delta x total? We've got this equation. This is adjacent, and adjacent is equal to hypotenuse times cosine of the angle. Y, the y-axis is opposite the angle, so we use hypotenuse sine for opposite. Sine of 40. Let's go ahead and plug those in. 50 cosine 40 and 50 sine 40. So when I do cosine, I get 38, but notice that is westward, so I'm going to make that negative. That's negative 38.3 kilometers. The delta y total is positive because northward, 32.1. Okay, those are our totals. So let me look at the x-axis first. Whoa. The total x, I'm going to take this equation, rewrite it. The total x is negative 38.3, I just found. And we got to that total by adding the x component here and the x component here. But the 20 kilometers has no x component because it's all on the y-axis. So this equals the x component of the second vector, that angled vector, whatever it looks like. We don't know yet. And now we know delta x2. It is negative 38.3. We do the exact same thing with the y-axis. The total we found was positive 32.1 kilometers. And we got that total by adding the y component from this with the y component from this. This y component is 20. It doesn't go on the x-axis. And from here we can find the y component of our second displacement. It's this 32 minus 20. Well, that's pretty easy, 12.1. So what have we learned? We have learned, let me take away that question mark. We've learned that this vector, whatever it looks like, is it like this? Does it look like this? Does it look like straight to the, the west? Well, let's answer that question right now. Whatever it looks like, it has a negative x component equal to 38. That's pretty long. Let me draw it like this. And it's pointing to the west, negative. And whatever it looks like, it has a positive y component that's shorter. It's only 12. Okay. 12.1 kilometers. So the hypotenuse is this second displacement. There it is. We have to find that hypotenuse. We have to find the angle. We use Pythagorean theorem to get the hypotenuse. And so, let's see, I'm like running out of room here. And we do 38.3 kilometers squared plus the 12.1. We have to square root it to get the hypotenuse alone. And second square root, 38.3 squared. I drop all negatives because I know they're going to go away anyway. If I square value, it becomes positive. And this equals 40. 40 kilometers. The angle is the inverse tangent, so tan to the -1 of, that means of is parentheses, so theta equal sign tan -1, and then I do opposite over adjacent. If I leave the angle, I hit the opposite leg, that's 12.1. Again, I'm dropping any negatives when I calculate the geometry of the triangle. This is 38.3. And what do we get for theta? Second, tan, 12.1 over, 17.5 degrees. Now I marked my theta at the x-axis, right here. So I'm going from the east and I'm pointing to the hypotenuse, the vector. So of east, it's to the north. West. It's north of the west. North of west. We can't put n of e because the n would look like newtons. All right, all done.